pastoral programs and 1 professional program. We had professors and associate professors among lecturers, with excellent reputation in scientific research and publication. There are also 65 laboratories to support educational and research activities by the lecturers and students. We are committed to continuing to improve the competence of lecturers and students, especially in facing the era of digitalization. The 9 departments under the Faculty of Engineering are
Professor Kenji Yasuoka as our guest lecturer.
Civil Engineering Department,
Mr. Renato STMD PhD, Secretary of Department of Mechanical Engineering of Kuliah University. Faisal Wahyudiansyah, Head of Mechanical Engineering of Zoom Association. Assalamualaikum warahmatullahi wabarakatuh. Salam, Om Swastiastu, Namo Buddhaya.
Mechanical Engineering Department,
Good morning, everybody. It is a pleasure to welcome you all again for the second installment of today's guest lecture with the theme of molecular simulation and its application. Yesterday, we've already had the first part of the guest lecture in which we covered all the basics, and today we are going to witness a demonstration of the molecular simulation. And we're going to learn more about its application. It is a great blessing for all of us to be able to gather here today to witness the advancement of technology. And as such, let's all take a moment to raise our prayers to God Almighty collectively in silence. Thank you. Now that we have proceeded with our prayers, without further ado, I would like to proceed and give the floor to our guest lecturer and commence today's event. To Professor Kenji Yasuoka, you may have the floor, and Professor Renato, as the moderator, you may also have the floor. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, Bapak Ibu and all students. Thank you for your coming for today's lecture. So today is the last session of our lecture on molecular simulation, and today Mr. Yui Ono will present his research and then will show us how to perform molecular simulation. Mr. Yui Ono is a PhD student, the second year of PhD student at Mechanical Engineering KU University, Japan, at Professor Kenji Yasuoka lab. Okay, please. Mr. Ono, present. Now it's time is yours. Thank you.
Good morning. Hello. And I'm Yui Ono, and I'm a PhD student, second grade of the PhD student of Department of Mechanical Engineering, KU University in Japan. And so, right figure is right person is me, and center person is Yasuoka, Professor Yasuoka Sensei. And today I talk the 2 topics, and the first is about my research, and my research is water ethanol separation with deep charged carbon nanotubes. And second, I demonstrate GLOMAX. GLOMAX is one of the famous molecular dynamics simulation software. And okay, and so I start the talk about my research, and my research is water ethanol separation with deep charged carbon nanotubes. And the main topic of my research is water ethanol separation, and everybody knows ethanol. Ethanol is one of the most important industrial organic substance, and in recent years, bioethanol bioethanol becomes more important as an alternative fuel, And when using ethanol as a fuel, we have to use anhydrous ethanol. Anhydrous ethanol is pure. Pure means the completely water removed ethanol. However, the ethanol concentration of the bioethanol produced by fermenting is only about 10%, so very low. So separation of the water and ethanol is necessary for bioethanol. And the general method for the separation of water and ethanol is distillation. Yeah. Especially, we have to use special distillation called azeotropic distillation for getting anhydrous ethanol. But this azeotropic distillation consumes a lot of energy. So improving the water ethanol separation process is important. And we have approached water ethanol separation using the carbon nanotubes. And carbon nanotubes is a cylindrical substance composed many carbon atoms, and its diameter is several dozen nanometers, so very narrow and small tubes. And also, carbon nanotubes has many useful characteristics such as high axial intensity, semiconductivity, and cylindrical shapes. And one of the applications of carbon nanotubes is nanopores for separation membranes. And actually, it's an artificial carbon nanotube membranes for desalination or gas separation and so on has already been proposed. And in the previous research, so this research is this is Dr. Benedetto's work, and water ethanol separation method, new water ethanol separation method was proposed by using an external electric field and carbon nanotube. This is using the combination of the carbon nanotubes and electric field. And this is a molecular dynamics simulation study, so I will demonstrate after. And left figure shows the simulation systems, and there is a water ethanol solution on both sides of the carbon nanotubes membrane. And without electric fields, ethanol molecules occupy the carbon nanotubes. But under electric field, water molecules occupy carbon nanotubes. So this phenomenon is useful for water ethanol separation. And in this study, we propose to improve the water ethanol separation method by using tip-charged carbon nanotubes. The tip-charged carbon nanotubes refers to the carbon nanotubes that has positive charge at one tip and negative charge at the other tips, like this figure. And actually, some functional groups, such as ionized carboxyl group and so on, have charge. So in these tip-charged carbon nanotubes, electric fields generate spontaneously by tip charge. So we use this electric field. So this carbon nanotube will make possible to achieve the water ethanol separation without an external electric field. However, the electric field generated by tip charge is much more complicated than artificial external electric field. So in this study, we have set the following two purposes, and we investigated the two contents. The first is water structures under electric fields caused by tip-charged carbon nanotubes, and second is behavior of water and ethanol molecules under electric fields caused by tip-charged carbon nanotubes. And I use classical molecular dynamics simulation. So this method, we solve the simple Newton's equations of motion of each particle, each atoms. And for example, we use non-bonding interaction. It means interaction between the atoms and non-bonded atoms. And so I use the non-bonded interaction. This is expressed as a summation of the Rand-Jones potential and Coulomb potential. And the temperature. So in the molecular dynamics simulation, we set the temperature and pressure. And I set the temperature and actual pressure controlled at 300 Kelvin and 0.1 megapascal. And for ethanol molecules, the hydrogen atoms in the hydrocarbon chain are omitted, as shown in the upper right. This is one of the model of the ethanol molecules in molecular dynamics simulation. And the carbon atoms at the tips, for the tip charged carbon nanotubes, the carbon atoms at the tips are replaced with charged carbon atoms, as shown in the lower right. And this is a simulation systems, and the carbon nanotubes length is 3 nanometer, and the total length of the simulation, total length of the system is almost 15 nanometer. And we calculate the many systems changing the carbon nanotube diameter, whether the number of charges or amount of charge. And then I show some results. And in this research, the intensity of electric field is important. So we calculated the electric field in carbon nanotubes. And this figure shows the intensity of the Z component of electric field on the center line of the carbon nanotubes. The left is in small carbon nanotubes, and the right is in medium carbon nanotubes. And the gray region also. Gray region, I mean the inside of the carbon nanotubes, and the white is outside of the carbon nanotubes. And the figure shows that very strong electric fields from the several volt per nanometer to dozen volt per nanometer are generated inside the carbon nanotubes by tip charge. And in addition, the electric field is non-uniform and the reverse outside of the carbon nanotubes. And so next, I show the snapshots in the carbon nanotubes. These show the structure of water in carbon nanotubes, and the left is small carbon nanotubes, and the right is medium carbon nanotubes, and the rectangle image. So the water structures in rectangle is a development of the cylindrical structure. It's how to develop it shown in the right small. And in small carbon nanotubes, the water molecules are aligned in a straight line. And so this shows a helical structure. On the other hand, in right figures, water molecules don't become to so order. Yeah. So helical structure was not found in the medium carbon nanotubes. And next I show the result of the radial distribution function. This is the function shows the density in each cylindrical slice obtained by slicing carbon nanotubes into some rings, like right figure. And the average distribution of the molecules in carbon nanotubes is shown in the red line. Yeah, but I divided carbon nanotubes to 6 regions and also calculate radial distribution function on each 6 regions. And the left shows the radial distribution function in small carbon nanotubes, and right shows in medium carbon nanotubes. In the case of the right figure, there is a high peaks, right medium. In the case of the right medium carbon nanotubes, there is a high peak in the dark green line, and the region near this dark green line is a radial distribution function and near the negative charge, and we could find such a circular water structure as shown in this figure. And this ring local structure was not formed in the vicinity of the positive charge. So the electric field is symmetry, but the structure is not symmetry. Yeah, this radial distribution function shows that. And the next, I show the electric field in the charged carbon nanotubes by tip charged and water molecules and the summation of both. And the blue line shows the electric field by tip charged, and the green lines shows electric field by water molecules, and the red line is the summation of both. And the electric field by the tip charge is positive and not flat. So blue line is positive and not flat. And on the other hand, the green line, the electric field by water molecules are negative, and the shape is to counter the electric field by tip charge. And the total electric field, red line, becomes flat and weak. So in the water molecule orderly aligned, the green electric field is expected to be flat. In other words, this means the non-uniformity of the electric field by tip charge is considered to disrupt arrangement of the water molecules. Next, I show the simulation result of the water and ethanol mixture systems. And first, this is a snapshot of the snapshot in the carbon nanotubes. And the yellow molecules shows show water molecules, and the green molecules show ethanol molecules. And the upper figure shows the change of the diameter, and the lower figure shows the change of number of charges. And we can know that when the diameter is too large or too small, ethanol molecules, green molecules have existed in carbon nanotubes. And also, if the number of charges a lot, only water molecule exists. So yellow molecules exist in carbon nanotubes. But if the number of charges small, number of charges zero, almost no molecules exist. And this shows the mole fraction of water in carbon nanotubes. And the horizontal shows the diameter of carbon nanotubes, and the vertical shows the mole fraction of water in carbon nanotubes. The mole fraction is the ratio of number of ethanol molecules and the number of total molecules. And the difference between each line is the number of charged or charge amount. And the mole fraction of the entire system is dot lines, 0.2 line. So the difference from this dotted line is important. This difference is a change by charge. And as you can see, tip carbon nanotubes have high selectivity in the area in the in terms of the diameter from the 1.2 nanometer to 3 nanometer. And so when the diameter is too small or larger, the selectivity decreases. So if we separate water and ethanol, we should use medium size, medium diameter carbon nanotubes. So, and so this is a conclusion. And so I talked my research about my research briefly. Or if you have any question.
Okay, I have a question. So, in the system, you use a chart at the tip of the CNT, and the chart induces not uniform electric field. And I mean, if we compare with uniform electric field, what is the effect of separation effect for water and ethanol? Which is stronger, with uniform electric field or with electric field generated with a chart at the tip of the CNT? So you use a chart at the tip of the CNT to generate electric field, and the electric field in CNT is not uniform.
Yeah.
Right? If we compare with uniform electric field, I mean, because you want to have a separation effect, right? If we compare with uniform electric field, which is the stronger separation effect, with uniform electric field or with your system? I mean, do you understand? What is different? What is different with system and my system?
Yes. Yeah. So, yeah, in this snapshot, the bottom of the please see the left development figure. So the bottom and top of top water molecules disordered. So this caused by the electric field direction. So when we use the external uniform electric field, the direction and intensity of electric field are flat. But in this case, at the entrance of the carbon nanotubes, electric field becomes zero, and this means the electric field direct to non-axial direction, completely non-axial direction. And so these difference of the electric field cause that the disorder of the water molecules.
Okay, thank you. Maybe someone have a question? Yes.
Okay. まずは本当にありがとうございます for your explanation. My name is Adi Dirgara Hakbau and I'm from Faculty of Mathematics Science and Natural Science, Department of Chemistry. I saw that you use acetic functional group on your tip of your carbon nanotubes, And my question is, have you ever tried another functional groups on the tip of your carbon nanotube? And how the effect of the use of the ion on the tip of the carbon nanotubes? Thank you. Assalamualaikum warahmatullahi wabarakatuh.
So, in this simulation, we treat the functional group is one particle. So there are, we can't express the difference of the functional groups. And but if we attach the more weak functional group at the tips, maybe it may disorder the flow and the structure near the tip near the entrance of the carbon nanotubes. So in this simulation, I didn't try the difference. I didn't try several functional groups. So
It's okay. Another question. No more question. If no more question, Mr. Ono will
okay.
how to
The
perform simulation. Yes.
okay, I start. And okay, I start the demonstration of GrowMax, and I make the document, and so and some links, some important links are pasted in this document. And first, today I introduce the software GrowMax, and GrowMax is free and open source software for high performance molecular dynamics simulation, and so free is important. And also GrowMax is a character user interface. It's a CUI software for Linux OS. So first we have to know how to use Linux. So first I explain briefly how to use Linux OS and how to install the Linux install briefly. And so I demonstrate the GrowMax. And so we cannot operate GrowMax with mouse and clicking some buttons because the GrowMax is CUI. So we just operate with write command. So we should write command for operate GrowMax. And so first, it is difficult to use at first, but GrowMax is fast and multifunctional. So, and first I talk about the environmental constructions and Linux OS for GrowMax briefly. And this is required because GrowMax is Linux only software, so we have to use Linux at first. And Linux, so maybe I think これで左は後で大きくします。あ、右もですか。G を大きく。どこだっけ。ちょっと忘れましたね。ズームインにも。Okay. And okay, and so I explained maybe I think that most of everyone in here is not don't know Linux OS well. So I briefly explain the Linux OS, and Linux OS is also free and open source operating system. The typical servers for calculation and communication and other service open Linux OS. And so, for example, the most OS of supercomputing are based on Linux OS. So if you use supercomputer, you have to know about the Linux OS. And then I don't explain the details of the installation of the Linux OS, but if you use the Windows PC of Windows 10 or 11, you can use easily Linux OS through the WSL means the Windows subsystem for Linux. And if you use the Mac OS, actually Mac OS is based on Linux OS, so we can use terminal software, which is almost the same as Linux OS by default. So if you use the Windows PC with earlier version than Windows 10, it is a bit complicated to install. And so I paste some links for like this. So yeah, and there are many websites for installation of WSL. So you can see these sites. And next, I talk about the basic use of the Linux OS. And in the most case in Linux OS, we control OS using CUI. So left window is CUI. It is called terminal. So this is we control the OS from this terminal. And so if you open the WSL or terminal, so you can see such kind of the window, left window. And then we put type command and operate OS. And I show the basic command of the Linux OS here. And so for example, the ls command is show files and directory on current directory, so here directory. And so this is like, so if I put the ls, we can get some results. One is the EMMDP or EQB MDP or system grow at top. So this is files on these directories. And so there are many commands in the Linux, but basic commands are here. And so if you have the Linux OS, you can install the GROMAX very easily. And so if okay, yeah, we can. So this command is the install command for the GrowMax, and I input this. No. So they demand password. And so I already installed the GrowMax, so yeah, but you can install the GrowMax only this one command. And so if GrowMax is also CUI, so we have to use command for operate GrowMax. And so the main command of the GrowMax is gmx. So if we put gmx, there are many informations for about GrowMax. And GrowMax can perform various operations by the subcommand following gmx. And for this is a website of the GrowMax. We can see the many commands. So this is a documentation page. So there are many commands. And today I use some commands in this, but I don't explain all the command. And so in this situation, you can use the GrowMax and you can do the molecular dynamics simulations. And so next, I prepare for simulations, and we have to prepare 3 types of files for GrowMax simulation. The one is the GRO grow file, and this grow file is a system configuration file. And system configuration means particle coordinates or particle velocities. And next, second is a TOP file, topology file. And this is a parameter of particle interaction, so such as a van der Waals parameter or charge amount or bond parameter. And finally, third type of the file is a MDP file. This is a simulation setting file, and this file includes a simulation time, temperature, or pressure, and the boundary condition. So in this, okay, and in this demonstration, I simulate the system with 18 crown 6 molecules in water works. So I have already prepared these files, and yeah. So I show the file. And so this is a grow files, and this so this is a text file. So we can read and edit. And so this first line is a title, and second line is a number of molecules, number of particles, and this is a molecular ID and molecular name and atom name and atom number and coordinates. So we can also see this format from this link. Yeah. So these files are these files is formatted. So we have to make these files. You have to make these files for obey this format. And so grow file is these molecular coordinates or molecular type, molecular atom type, atom coordinates, atom velocity. Yeah. And next, the topology file. Topology file is show. So I show the topology file is such file, and this file includes a parameter. Parameter is such as mass of the particle and the mass charge of the particle, or some van der Waals parameter for particles, and bond length and the bond parameter. Yeah, and so today I prepare this file, but if you want to do simulation, so you can make or get from somewhere these files. And so this system grow file, so this is only text based, but maybe you want to see this file. This file means what configuration. So, and we can use some visualization software for visualization these files. And I show this file. And so now, so this is a configuration in Grow files. So there are many water molecules, and there is one other molecule. This is 18 crown 6. Yeah. So I prepared this file, and if you want to simulate, you also prepare this file. You have to prepare. And next, I run the simulation, and we also have the two MDP files, and MDP file is a simulation setting file, and one is EM MDP. And first I run the energy minimization, and next I run the NVT MD simulation. And for running simulation, we use to command grow MPP and MD run. And so grow MPP command is combine and convert three type of files: the grow file and the top file and MDP file to convert to TPR file. And yeah. And for energy minimization, we use this EM MDP file. And so this is MDP file is a simulation setting file, and so there are many settings. And so, and for example, this N step is the step of the energy minimization. So now I run this energy minimization, and so put this command, and we can get a new file. It is EM TPR, and you can run the simulation this command. And now I run the simulation. And we can get some result. Yes, but now I run the simulation, but it is no interesting result. Next, I show the NBT simulation. We can see the trajectory in this simulation. And so next, I run this NBT simulation. And we input the I input this EM.grow. This is a result of the energy minimization. And I make the EQB TPR and run simulation. And this simulation is spends some times, now simulating. It's a bit wrong. Okay. Maybe in this PC, maybe some process using the CPU. Yeah. Okay, simulation is done. And we can get some result, EQB, blah, blah, blah. And so this EQB grow is a configuration file, and EQB TRR is a trajectory file. And I will see this trajectory now. So this line is so bit strange, but this is we can see the molecular moves like this. Sorry, I remove the line. So, yeah, and this is you can know the move of the molecules. And yeah, and so in this system, there is one special molecules in water bottles, and we can see the trajectory of these molecules. Okay. Today I use visualization software BMD. So I paste some information for BMD. And in the GrowMax, we also see we also get some physical quantity using command. And put this command. There is a list of the physical quantity, and now I use the potential energy. So I put 8, and so then GrowMax makes energy XVG, and we can see this. We can see this file to as graph. So like this. So this is a potential energy of this simulation. So this is a easy flow of the GrowMax. And I also introduced LAMPS. LAMPS is another one of the most famous free molecular dynamics simulation softwares, and LAMPS is highly scalable and can perform Reax force field, which can model bond fermentation and breaking, and so on. So this is also CUI software for Linux, same as GrowMax. So this is the end of the demonstration.
Mr. Ono sudah menjelaskan tadi bagaimana cara menggunakan GrowMax ya. Jadi salah satu software yang sangat populer untuk simulasi molekuler itu adalah GrowMax gitu ya. GrowMax itu salah satu software yang cukup cepat, dan untuk bisa menggunakan GrowMax itu harus familiar dengan Linux gitu ya. Jadi Linux command harus harus familiar dulu gitu ya. Jadi harus familiar dulu karena memang GrowMax itu harus pakai Linux gitu ya. Jadi kalau kita perintah di Linux itu tidak bisa ya harus itu dulu gitu ya. Itu sebenarnya tidak sulit gitu ya, tidak sulit. Jadi juga artinya untuk bisa menjalankan GrowMax itu ya hanya beberapa perintah yang harus kita kuasai gitu ya. Itu ya sebaiknya hafal, tapi kalau di awal-awal biasanya belum hafal, bisa lihat ininya gitu ya, listnya bisa kita lihat gitu ya. Jadi tidak sulit. Terus nanti setelah beberapa kali kita pakai, biasanya juga kita hafal sendiri gitu ya. Gitu. Jadi tadi Mr. Ono menjelaskan beberapa perintah di Linux. Kemudian berikutnya menjelaskan GrowMax. GrowMax itu adalah software yang free gitu ya. Jadi free, terus di situ juga ada manualnya ya, panduannya gitu ya, penjelasannya GrowMax itu seperti apa gitu ya. Terus tadi Mr. Ono juga menjelaskan bagaimana cara menginstallnya gitu ya, install GrowMax gitu ya. Berikutnya menjelaskan setelah kita install bagaimana cara menggunakannya gitu ya. Jadi kalau di GrowMax itu ada 3 file yang harus kita siapkan sebagai inputnya gitu ya. Jadi ada grow file tadi gitu ya. Kemudian ada grow file itu adalah konfigurasi awal dari molekul kita. Jadi sebelum kita mengeran simulasi, kita harus menyiapkan sistemnya gitu ya. Sistemnya seperti apa gitu ya. Jadi kalau tadi risetnya Mr. Ono kan ada karbon nanotube, kemudian ada air, ada etanol gitu ya. Jadi saat awal itu posisi dari setiap atom karbon nanotube itu di mana saja gitu ya, pada koordinat berapa saja gitu ya. Jadi semua molekul yang ada di sistem kita itu kita harus tahu posisinya di mana, itu harus kita siapkan gitu ya. Itu di grow file tadi. Kemudian grow file, kemudian tadi top file gitu ya. Top file itu isinya adalah parameter-parameter yang kita perlukan untuk simulasi. Karena setiap molekul antara molekul satu dan lain itu kan ada interaksi gitu ya, ada tarik menarik. Nah itu seberapa besar, seberapa kuat tarik menariknya itu ditentukan oleh parameter-parameter itu. Nah itu parameter-parameter itu dimasukkan di top file tadi gitu ya. Jadi sudah dua. Kemudian yang ketiga adalah MDP file gitu ya. MDP file itu adalah isinya parameter-parameter untuk mengontrol simulasi kita. Misalnya kita ingin mensimulasikan pada temperatur berapa gitu ya, pada tekanan berapa, itu semuanya di set di MDV file tadi gitu ya. Jadi setelah ketiga file itu kita siapkan, kemudian kita bisa langsung kita run dengan GrowMag gitu ya. Tadi untuk nge-run GrowMag itu tahapnya ada dua. Jadi yang pertama tadi MD grow gitu ya, itu akan menghasilkan beberapa file hasil dari running pertama tadi, kemudian dipakai untuk running yang kedua yaitu MD run tadi gitu ya. Dari MD run nanti keluar hasil gitu ya, termasuk energinya berapa tadi yang ditunjukkan tadi energinya gitu ya, termasuk nanti molekulnya itu kan bergerak itu ya, bergerak ke ya dari kondisi awal tadi karena ada interaksi ini masing-masing akan bergerak itu ya. Nah bergerak nanti posisi dari masing-masing atom dari waktu ke waktu itu disimpan di TRR file. Tadi ada file TRR itu ya. Itu TRR itu isinya adalah hasil dari simulasi kita itu ya. Itu kira-kira. Terus untuk memvisualisasi setelah kita dapat hasil simulasi, untuk mensimulasi tadi Mr. Ono pakai software VMD gitu ya. Jadi VMD itu untuk mensimulasikan tadi kalau ada molekulnya yang ya, seperti itu tuh VMD gitu ya. VMD itu juga free gitu ya, bisa di download free gitu ya. Dari VMD nanti bisa kelihatan seperti apa itu gerakan dari molekul gitu ya. Seperti itu. Kemudian selain GrowMag ada software lain selain GrowMag gitu ya. Tadi ditunjukkan ada LAM tadi ya. LAM itu malah bisa untuk dari kalau misalnya ada atom ingin kalau atom supaya terbentuk molekul itu kan harus ada bonding ya, jadi formation or bonding formation atau ikatan yang breaking ya, bonding putus itu ya, tadi pakai react ya, itu ya. Kira-kira itu ya tadi yang dijelaskan oleh Mr. Ono. If you have question please, silakan kalau ada pertanyaan. Ada yang tanya? Ya, silakan.
Assalamualaikum warahmatullahi wabarakatuh. My name is Amal Fasya from Mechanical Engineering Department. I want to ask about the software. What is the difference between this GrowMag software and then from that another one software? Is there any specification differences between that two software?
The difference of the software GrowMax and ramps.
Yeah.
GrowMax is fast, but it is optimized for the leakage simulation. Yeah, and for example, the protein in the water, something like and the ramps is I think ramps is used for the many used for the solid simulation. So there are different so GrowMax is optimized for leakage. So if you try, if you do something solid simulation, it is you cannot choose options. There are no options. Sometimes there are no options, but ramps you can. If you choose ramps, you can something. So there is a difference of the option and the scalability. Yeah.
Thank you for your presentation, Mr. I would like to ask about what the critical step if we want to use this software. What the critical step? And the second question, can we know the change of molecular structure if we simulate some intermolecular interaction between two molecules using GROMACS?
Your question is, the first question is you mean the minimum specification of a computer to run with GROMACS. So is there any minimum specification of our computer?
Oh, what specification?
For GROMACS. I mean, if we want to install GROMACS in our computer, is there minimum requirement of our computer to the hardware? Yes, hardware. Minimum specification of hardware.
The critical step or the critical instruction if we use GROMACS, like what the kind of command we should to input in this software if we want to running one simulation.
For example, this computer has 12 CPUs, and so but this is not fast one, so it is not so high spec. And if you use the okay, in my simulation, it's I talked previously the water ethanol separation simulation. In that case, I took the about three days for one systems, and so that is maybe 10万ぐらいじゃないでしたっけ 10,000 atoms. Yeah. And use the 10,000 atoms. I ran the simulation of the 10,000 atoms without GPU, the time is almost 3 days, about 3 days. Yeah.
How many nanoseconds?
Yes, yeah, 10 or 15 nanosecond. Yeah.
10 nanoseconds.
Yeah, yes.
So we run the system. The system consists of 10,000 atoms, and we run for 10 nanoseconds. It takes 3 days.
Yeah.
With your
Yeah. My research. Yeah.
with, and the specification of the computer is
Twitter is
how many cores is it?
yeah, maybe 12 core. Yeah.
With 12 cores. In part because the
Ah,
computation is
12.
parallel computation.
12,
We use
16 core. Yeah.
16.
Yeah. But if you use a GPU graphical mode, maybe simulation becomes more fast. But in my simulation, I can't use GPU, so my simulation is rate simulation, yeah. Right? Long simulations.
So the simulation is depend on our system. If our system contain many atoms, need longer time to get the result. Also depend on how many computer we use because the in the simulation we use we use computing parallelization. So it means that we Mr. Ono use parallel computation. So it means that he used some computer to calculate to perform the simulation. If we have many core, so the simulation will be faster. Something like that. Yeah. Actually, so we can perform simulation with our laptop, but if the system contain many atoms, it take very long time. But if our system is not so big, I mean the number of atoms is not so many, so it is so possible to run with our laptop. Any other question? Ya, silakan.
Thank you. Do you have any specific recommendations for resources or further readings for maybe any of the attendees here today who might want to try out molecular dynamics simulation on their own?
Oh, sorry.
Do you have any specific, is there any specific references or resources that you would like to recommend for if there are any students here who would like to try out molecular dynamics simulations on their own after this? Maybe if you could refer some books or maybe some articles, websites, or some general resources in general.
How do you resource? Recommend?
So it's if you have that some large money, it's easy. So maybe your question is if you would like to start the simulation. So what kind of the hardware do you need? So maybe your question is okay. So it depends on the size, system size. If maybe this one, how many molecules? Maybe
2,000.
Well, 2,000 atoms. But that's the 2,000 atoms. It's not of the large system, but still we can do that. There's several thousand system. Then, so he used only the laptop computers. That is, I think, not so fast. And also he knew that something more. Then you can do that. Yeah. Dr. Winaldo also use just a desktop Macintosh. So then also we can use that. Nowadays we use in many of them GPU machine. It's hardware like a game hardware, GeForce, RTX something. So then when we use several 10,000 example to 20,000 or 30,000 atoms, and include the water or protein, then we take it in maybe in one day, 1 nanosecond, 100 nanosecond. They're very fast. So maybe 10 times faster than his case. So it depends on the hardware. But if you started a small system, you can do that. Your laptop computers, well, don't worry. So, but that software is very fast. Is a GROMAX. That's why. So he introduced you that software. But I think it is not the GUI. It's easy software is just click, and then somehow you can use a mouse. So, but here, so you needed something in the type. So a little bit hard to use, I know, but it's very fast. So sometimes in the commercial software you can use in only the mouse. Then it's a little bit slow. So then we use such one. And then today, so if you have a very fast computer, doesn't matter. It's you can use a commercial software or maybe, but maybe you don't have so much in a computer then. So maybe laptop or some desktop computers, and then you can start. That software is very fast. Yeah. And then lamps is also the more flexible use. So sometimes he also explained that we use for the material, or so soft material or hard material something. Then it's a little bit slow, but we can use it. Yeah, we also use that. Yeah. It's okay. Your question?
Thank you.
So it is still possible to learn GROMAC with our laptop. So if we want to just learning GROMAC, we don't need to make a big system. So we just make a small system, and it is not, possible using our laptop to run the system with not so many atoms. Yes, I have a system, maybe the number of atoms is around 2,000, and I ran with my desktop for 10 nanoseconds, and it takes time less than 24 hours. So it's still possible to run with desktop. Any other question? Ada lagi? Silakan kalau masih ada lagi. Sudah tidak ada? If no question, I will finish the session. But if you want to discuss with Mr. Ono after I close the session, it is still possible. Jadi kalau ini akan saya tutup ya, kalau tidak ada yang tanya lagi. Tapi setelah saya tutup, kalau ingin diskusi lagi dengan Mr. Ono, silahkan gitu ya. Jadi silahkan diskusi informal gitu ya, gitu ya. Okay, thank you Mr. Ono for your presentation and explanation about what is Chromec and how to perform simulation with Chromec. Before I close the session, let's give applause to Mr. Ono. Okay, I give back to Kenji.
Thank you very much, Pak Wirnato. Thank you very much, Mr. Yueno, for the absolutely insightful presentation on molecular dynamic simulation. Before we close today's session, we would like to ask Mr. Yueno, Professor Yasuoka, and also Pak Wirnato, and as well as get a representation for the Mechanical Engineering Student Association to come up for a photo session up front. So please, sir, Professor Yasuoka, Mr. Yu Ono, let's come to center to take pictures. Yeah. Maybe the three of you first, and I might join later. Shall I?